The Raspberry Pi Compute Module 4 has a respectable little GPU. Its built-in Mali GPU core can push out 4K resolution over HDMI at 60 Hz. Well, under ideal conditions, if you're not pushing it much. But I had a thought. What if I wanted to run Crysis on my Raspberry Pi at 8K and 60 Hz? Well, that's why I bought this. This is an AMD Radeon RX 6700 XT, and it just came out a few months ago. And if there's any computing part that's been harder to get than a Raspberry Pi Compute Module 4, it's graphics cards like this one. When I mentioned I got this card, someone asked, how much did it cost?
Everything.
Well, at least I still have a shirt on my back. But I have to justify the purchase, so let's plug this card into a Raspberry Pi and see what happens. So first we need to unbox the card. I'll be honest, I haven't bought a new graphics card since 99, 2000, I don't remember. Whenever the Rage Pro 128 was the latest thing. So this is kind of a new thing, opening a new box and having to cut the seals on it. Usually I buy things used, so this is definitely a new experience. That's pretty spiffy. Whoa, things are jumping out at me. Okay, so they don't include a user manual anymore. That's fine because I don't read it anyways. All right, so here is the card, and it is very big, that's for sure. It's a pretty hefty card, and if you don't have a big PC case for it, it's a little bit unwieldy. I know I watched a Gamer's Nexus video on a teardown, and this backplate doesn't actually connect to anything with a heatsink, so I'm not going to do a teardown on the card or anything. Go check out that video if you want to find that. But this is the Radeon 6700 XT. I'm going to take off this little shield. And let's look at some of the specs for it. I know it's not the top tier card, but it's the latest generation of AMD's graphics cards. It has 40 compute units. That's the thing that I'm most interested. A lot of people ask, why would you care about something like this on a Raspberry Pi? And there's the first obvious answers. People like mining, not Bitcoin, but whatever kind of cryptocurrencies. Some people want to mine that. And the cheaper the computer, it doesn't matter. They just need to buy one slot to get the cryptocurrency to mine on the GPU. For me, I'm more interested in things like AI and machine learning. You can use a card like this and have it run basically extra compute power for things like machine vision and processing different data sets and things like that. And also now with Proton on Linux, you can actually game on these cards too. So if you could get a Raspberry Pi super cheap and then somehow get a GPU, maybe not this one, this is probably overkill for a Raspberry Pi. But if you could get a GPU and get it running on the Pi, you could run a lot of games that used to be Windows only on a Raspberry Pi.
So could I run Skyrim?
I don't know. It also has 12 gigabytes of memory, so I don't know if that's going to be a good thing or a bad thing. I know that in the past with the first GPUs I was testing, they had a gig or 2 gigs of memory, and the mapping in the bar space on the Pi wasn't working that well. So we're going to see if this thing will even map correctly, and if it does, then we can see if the driver will work. But I'm not super optimistic, but the first step is getting it unboxed, and we've been successful there, and it looks nice, that's for sure. A lot better than the little M.2 VGA card here. You can see that for size comparison, or you can even see the Compute Module 4. If we can ever get this working, somebody could build a backplane for the CM4 that maybe could be integrated directly into the backplate, and you could have your computer and GPU all in a GPU. Before I plug it in, I have to clear up a few things. The regular old Model B, which is what most people think of when you say Raspberry Pi, doesn't have a PCI Express slot. So you can't just go plugging random cards into it. And the Pi 400, well, no space there either. But this has a secret power. Instead of built-in USB 3.0 like on the Pi 4, it has an exposed PCI Express lane. Look, it's right there on the official I/O board. But we have some problems, some major problems. As my wife and I like to tell our youngest child, this ain't my first rodeo. First of all, the by one slot here is closed, so you can't just go plugging in a giant by 16 graphics card. It won't fit. I could cut the slot, but in my case, just because it gets a bit unwieldy, I'm going to use a PCI Express riser so I can plug the by 16 card into the by one slot. Second, power. The GPU needs 230 watts, and it has these two power connectors to get extra power since PCI Express slots can only put through up to 75 watts. So my normal way of powering the Pi, using this little 12-volt barrel plug adapter, won't work. Third, drivers. If you've seen my past videos on GPUs on the Pi, you might have noticed something. Every single card I've tested has locked up after I compiled a driver for it. Every one. Heck, last video I even tried this little guy, an M.2 VGA video card. It only has 16 megabytes, that's right, megabytes of VRAM, and even it locked up the Pi. So yeah, 3 big problems: the slot, power, and drivers. Let's see how far we get. All right, so the first problem is that we need to be able to physically plug this card with its gargantuan by 16 connector into the by 1 slot. And I could just cut this slot here, the back side of it. I actually have a whole video on doing that, and I'll link to that in the description. But since this card is so large and kind of heavy, it wouldn't be great to just stick it on top of the board. It would probably fall out of the slot just by gravity. So I have this by 1 to by 16 adapter, which I can just plug into the Pi and plug into the card. But that leads us to the second problem, which is power. This slot can only supply up to 75 watts of power to the card, and the card is rated as using 230 watts. Now, if we can't get it actually working, it probably won't use that much power, but it does have extra power connectors on the top. These PCI Express power connectors. There's an 8-pin and a 6-pin. So I have this Redragon RGPS 700 watt power supply. It's not the best power supply in the world. Again, hashtag not sponsored. This stuff all costs money. So, you know, making these videos, especially when you're not sponsored and these products are not free, costs a bit of money. So if you like what you see, or if I'm helping you out with some of this stuff, doing it all in the open, posting everything on GitHub, please consider supporting the channel on Patreon or GitHub. There are links in the description for that. But anyways, this isn't the best power supply in the world, but it should supply enough power. And the graphics card is going to use 20 times more power than the Pi itself. I think the Pi will use 5 or 10 watts. So I have this power supply. I'm going to plug it in over here. So it has power. And then I also have this jumper. If you use a power supply, a PC power supply, typically your PC has a motherboard that has a power button. The Raspberry Pi does not have a 24-pin power supply connector, and it doesn't have a power button. So someday I hope to have a Raspberry Pi PC desktop with a motherboard, basically. But until that time, I have to use this. This is my poor man's little switch. They have better versions of these, but this is one I hacked together in another video. Anyway, so there's our power supply, and we want it to power this card. So the power supply is fully modular, which makes it easier for me to work with on my desk. And it has this cable, which goes from an 8-pin to an 8-pin and 6-pin connector so that I can power this card. Some people use 2 cables, one for the 6-pin, one for the 8-pin. That's nice for spreading out the load over more wires, so you have less wattage over one particular wire. But it's not really necessary in this case, especially since I don't think that I will be using this card to its fullest potential. So I won't need all that power. So I'll plug the card's power in. All right, got those 2 connectors in. And then the next step is to power the Pi. In one of my earlier videos, I powered the Pi separately from the graphics card, and that's not a great idea to have 2 power supplies powering different parts of your system, unless you do special things like sharing the ground plane between them. And so you could do that, but in my case, I'm just going to power everything off this power supply. So I'm going to use this Molex cable, and I'll plug it into one of the 6-pin slots on the power supply. And then I'm going to plug in this adapter that goes from Molex to floppy connector. So I'm going to plug this in here and plug the other end into the Raspberry Pi to give it power. And of course this pin is coming out, so we need to get you back in there. And then I'm also going to plug in Ethernet so I can log into the Pi remotely from my computer. I'm going to plug the HDMI into the Pi directly because until we have a driver running, the card is probably not going to output anything. I'm going to try to turn this on and see what happens. The last thing that we'll need to do is get a driver working for the card, but it could be interesting just to see if it explodes when I turn it on. I know I wouldn't like that for my pocketbook, but it would make for good video. So let's see what happens here. So far, so good. Nothing's blown up yet. So it looks like the Pi booted up. Now, if I want to use the Pi, I actually need a keyboard and mouse. Luckily, I have one. But something else to note on the compute module, unlike other Pis, if you want to use the USB ports, you actually have to enable them in your boot config file. So I have a blog post about that. I'll link to it in the description. But if you do want to use these USB 2.0 ports that are built in, you have to do that before you are able to actually use the keyboard and mouse. So the first thing I'm going to do here is I'm going to see if the Pi can actually see that card. So I'm going to run sudo lspci-vvvv, and I'll make this full screen. And it looks like it's seeing something here. So it sees an advanced micro device, audio device, so that's audio over HDMI. Let's see what else it's seeing. A VGA compatible controller, so that's the video card, and let's see, the AMD device again. So it looks like it's seeing it. Now, if I look closely, there's no driver loaded, so there is no driver built into Raspberry Pi OS for it, and that's what I thought would happen, so that's not a surprise. I'm also going to go to dmessage and look at the PCI bus output. And I'm going to look in here and make sure that all the bar memory was assigned correctly. And it looks like all the regular memory assignments are good so far. There's no space for I/O, but that's okay because we don't need the I/O bar space for the ARM driver. So it looks like all the bar space was assigned correctly, and you can also see some of that output in the LSPCI output. So the hard part is that we need to get a driver working for it. It looks like hardware-wise everything's working, but the driver is going to be important if we actually want the card to be able to do anything, like be able to process stuff or be able to run games or anything like that. And just to show you, without a driver, if I unplug the HDMI on the Pi and plug it into the card, there's no output because the card has no driver, so the Pi can't even use it. So that's our next challenge. We need to install drivers for the card, and luckily AMD, unlike their primary competitor, contributes an open source driver right in the Linux kernel. Theoretically, all we need to do is compile a custom kernel and the driver will see the card and make it work. By the way, recompiling the kernel, I have a shirt for that, redshirtjeff.com. A lot of people have asked me how I recompile the kernel, so heck, let's do it live. So on my Raspberry Pi PCIe device website, I actually link to a cross-compile environment that I've built using Docker, which should work on any Mac, Windows, or Linux computer. I use it on my Mac, and it actually is compatible with M1 Macs, which is nice because the M1 is an ARM processor just like the Raspberry Pi. So you can compile ARM on ARM, and it's really nice. Every single step is listed in this README file. Like literally when I do this, I go to the README file and I copy and paste the commands and do it myself. So I'm going to do all that right here today so that you can see how I do it. So I have it up on my computer here. The first step is to build this cross-compile container image. So you run this command, docker build cross-compile, and it will download the base image from Debian Buster, and it will install some things on your computer for it, do all that kind of stuff. It takes a couple minutes. And once it's finished building the Docker image, the next step is to actually run that image. So I'm going to do that here using this command on the screen to run an instance of the Docker image. Paste that in, and now it drops you into that Docker image. So this is in a build environment that's customized for building the Raspberry Pi Linux kernel. And the next step is to actually grab Raspberry Pi Linux from the Raspberry Pi Linux repository. Now, if you're going to build a custom version of the kernel and do some specialized things, you might want to clone something else or clone a fork of the repository that you have in your own account with some patches applied to it. That's all great, and if you know what you're doing, you can do that. But for most cases, you just want to grab the kernel source from here and download it to your computer using Git. All right, and once the source is downloaded to this container, you can run these two commands to generate a config file, and I'll tell you about what that is in just a moment. This is going to generate a .config file that tells the Linux kernel build process, how to build it for the Raspberry Pi. So you can see at the end here it says BCM 2711 defconfig. These are the definitions that the Raspberry Pi Foundation has set up for that processor, that system on a chip that will make the Raspberry Pi run Linux correctly. So we're going to do that, and it generates this config file, and if I say cat.config, you can see that it generates this file with all these different options that are specific to the Raspberry Pi to make sure that it runs Linux correctly. But you can change that config to build the kernel in the way that you want. So in our case, we want to build a kernel with the AMD GPU driver. So what we're going to use is a utility called menuconfig. And you could do this by hand. You could edit that config file, but you have to know all the different flags to set and things. Menuconfig is a little quote-unquote graphical user interface that lets you scroll through and find the options you want. So in our case, I'm going to go to device drivers and then graphics support, graphics support, and then AMD GPU. I'm going to save this, and it writes that configuration out to config, and then I'll exit here. Now it's time to actually build the kernel, and this is going to take a little time. In this command here, I have a note in the README that this command can take different arguments depending on what kind of computer you have. You can have more jobs for it if you have more processor cores to spread the load out. And no matter what your computer, this parameter can be a little bit different to make it faster. This is optimal for my M1 Mac Mini, but it might be different. You could get it to be a little faster on your computer. If you have, let's say, a Threadripper, you could probably do -J 16 or 32 or something like that. So this is the longest part of the process. I'm going to go ahead and let that run, and you can see what it does. All right, so the kernel is compiled, but now it's on my computer, my Mac Mini, but it's not on the Raspberry Pi. So the next step is to actually get it over to the Raspberry Pi. And the way that I like to do that, the simplest and most convenient way right now for me, is using SSHFS to copy everything over SSH as if the Pi were mounted locally on my Mac. So the first step to do that is to, on the Raspberry Pi itself, set up SSH so I can log into it as the root user. By default, this is disabled for security reasons. So this is not something that you'd want to do on a production Raspberry Pi. You'd want to do it other ways. But for convenience, I'm going to set this up. And this Raspberry Pi is not doing anything online, and it's going to be erased afterwards. So I don't care about the security too much right here. So on the Pi itself, I'm going to edit the SSHD config file and then restart SSHD. So to do that, I'm going to go in on the Pi. So I need to open up a new terminal window, SSH into Pi at 10.0.100.109, and then I'm going to edit this file, and I'm going to go to permit root login and set this to yes. And then I'm also going to comment out at the bottom this password authentication no. Just for convenience, I'm going to use the root password. And to do that, I also have to sudo su to switch to the root user account. And then I'm going to say password, PASSWD, and set a password. I'll say raspberry. Okay. So now at this point, I should be able to, on my other computer, log in as root. I also actually have to restart SSH on the Pi. So I'm going to do that here. And I can exit out of there. So I'm going to try SSHing into that Pi, and my Pi's IP address is .119, but you could also log in using a domain name if you want to log into it as CM4.local or something like that, but I just use the IP address because I know that that's always going to work for me. So I'm going to try logging into it from here, and it's going to ask me about the authenticity of the host because it's the first time it's connecting. So I'll say, yes, I would like to connect to it. Then type in the password raspberry. And now I know that I can log into it from this Docker container. So I'm going to go out of here, exit, because I don't actually log into it. I want to mount a file system onto the Docker container from the Pi. So to do that, there's these 4 commands. First, you have to make a directory to mount it into. So I make that for the ext4 file system. And I make another directory for the FAT32 file system that has the boot partition. And then I'm going to use SSHFS to mount the Pi into these 2 places. So there's the first one. And this, whoops, I forgot to put the password in. So let me try that again. And then the second one here, and enter the password. Okay, so those two file systems are mounted. And if I look in here, I can actually see what's inside. So if I say ls that, this is actually listing the contents of the Pi itself over the network. So this is just convenient for me to copy everything over. So the first thing I'm going to do is install the kernel modules that I compiled. So I'm just going to copy this command and paste it. Am I in the wrong directory here? Okay, so it looks like in the compile there was actually an error here. Are there any other errors that I'm missing? That's interesting. I guess it could be that there's a bug in Linux itself, and I know somebody on Twitter actually mentioned to me that there might be a bug with the kernel version 5.10 and the AMD GPU driver on ARM, and it looks like I might be running into that here. So that could cut this short. I'm going to do a little more research and try to figure out if I can get a different kernel version to compile, or if I can get a patch to make it so that I can compile this. So it's looking like it could take a little time and might be a lot more effort than I first thought, trying to get this card to even lock up the Pi. So what I'm going to do next is I'm actually going to reset my build environment completely. So I can do that with git reset -- hard and git clean with these flags, and that'll clean out all the junk that I just built, and it actually didn't build all the way, which I didn't notice. And then I'll do it again, but I'll do it on a different branch, or I'll try different patch sets and things that I find online. All that information will be posted in this issue on my Pi PCI Express card database GitHub repository. But it looks like the kernel compile is not going to be quite as easy as it normally is. And you know, I think that I'll be able to say that it's been 0 days since I recompiled the Linux kernel. Go ahead to redshirtjeff.com for that. And I'll be able to be wearing that shirt quite a bit in the next week or two as I get into this card. So it looks like the recompile won't be easy, and I don't want this video to go too long, so I'm going to wrap it up there, but not all the news is bad. Not only do we know the bar space is no longer an issue, GitHub user CoreForge has been getting more and more functionality out of the older Radeon card he's testing. At this point, we've narrowed down the bugs to memory access errors, and I'm hopeful at least older generation video cards will work in some capacity. It's just a matter of time. I'll continue testing the card, so follow the GitHub issue for progress, and until next time, I'm Jeff Geerling.